8 2020 mechanical metallurgy. The number of independent elastic constant of an isotropic materials is 2. Okay. Let's see some concept which is related to elastic constants. When the two components which are typically Young's modulus and Poisson's ratio are the combination, alternatively, the combination of shear modulus and bulk modulus also can be used to describe the elastic behavior of a isotropic material. And even the shear modulus and bulk modulus, there is a relationship between Young's modulus, relationship between the shear modulus and bulk modulus. So even these two can be used to define the elastic component constants of an isotropic material. So that's why it depends on two. When you come for anisotropic material, general anisotropic material, there will be nearly 21 independent elastic constant. Okay. In a 6x6 matrix, you'll see these diagonal elements will be different and this upper and lower triangle elements will be same. So you can consider only one of this. So you'll be getting totally 21. And for an orthotropic elements, there will be 9 independent elastic constant elements. And they're generally the 3 mutually perpendicular planes of symmetry will be there. For it, transversely isotropic materials. Transversely isotropic materials is nothing but the in a plane, they will be having isotropic properties. So consider a plane stress or plane strain condition. So totally for these, there will be 5 independent elastic constant. Okay, for a cubic material, you will be having totally 3 independent elastic constants, as it is isotropic in all the 3 directions. Now, the slip system consists of slip plane and slip direction, where which one of the following is not valid for a slip system in FCC copper crystal. We know in an FCC copper crystal, the slip plane and slip direction, if you want to check, you need to see whether the plane and direction should satisfy the condition of this. If you check first option, 1 bar 0. So this is 0. And for second one, it is 0 plus 1 plus 1. This is not equal to 0. And third option, 1 plus 0 plus 1 bar. This is equal to 0. And fourth option, it is 1 plus 0 plus 1 bar. This is 0. So only option where it is not equal to 0 is this one. So this plane does not satisfy, or this is not a valid slip system in a FCC copper crystal. For a material to exhibit super elastic properties, the one requirement should be, it should have the coarse grain structure, high strain rate sensitivity, low strain hardening exponent, and high modulus of elasticity. The main property is high strain rate sensitivity. M should be very large. Strain rate sensitivity is defined by M, and it should have fine grain structure in the microstructure. The heavy cold metal will yield a coarser recrystallized grain size, no. Possess a lower driving force for recrystallization, no. Have high energy barrier for nucleation of recrystallized grains, no. And it recrystallizes at lower temperature. For a cold work material, you will be seeing that there will be a lot of strains induced in the material. So for this, the driving force will be large, and also recrystallization happens at a lower temperature, which is less than 0.4 times of Tm. This is called as recrystallization temperature. Lower than recrystallization temperature itself, it happens. And you yield a very fine grain structures. The components subjected to tensile stresses in a mechanical device is monitored periodically by cracks by NDT. The NDT technique can only detect cracks, both surface and internal, where larger than 1 mm. So keeping a margin of safety of 10%, the maximum load allowed tensile stress on the component will be. Here, The fracture toughness K1C is given by 30 meter. Okay. We know K1C is equal to sigma max root over pi c. Here it is, this is the stress we need to find out. This is given as 30 and this is sigma and root over pi. C is given as the detect a crack, both surface and internal surface. So let's see for an internal crack itself, C is equal to 0.001 meter. So putting this value, so you get sigma is equal to 30 by root over pi under root of pi into 0.001, you get 535.23 ampere. Now, considering the factor of safety is nothing but in an industry, if you see, the theoretical stress is this much, but the industry consider the factor of safety such that below this itself, they'll be using the material for the properties. So what they'll do is, the factor of safety is nothing but sigma max by sigma allowed, which is equal to 1 plus whatever safety they are following is equal to 1.1. So sigma max by 1.1 equal to sigma allowed. So here it is sigma max 535 by 1.1, which is nearly 486.5 ampere. Then edge dislocation, the configuration given in the figure, dislocation X and Y are fixed and separated by distance 2h on the same slip plane. Dislocation Z is free to glide on the parallel slip plane. The two slip planes are separated by a distance h. Which one of the following is true regarding the dislocation positions? 1, 2, 3. Now, assuming the dislocations are identical Berger vectors, if you'll see the position 1, two dislocations at an angle 45, it is stable at this position. But if you try to push it this way or this way, it continuously moves away from this point. So it becomes an unstable position, unstable equilibrium for it. And along with 45 degrees also, it is 135 degrees to Y position also. Though it is stable at this position, pushing it either side, this will move away from the first position directly. So that is why even though net force is 0, this is an unstable position. Now, for position 2 itself, X, which is less than 45, this is definitely an unstable position. And for Y at position 2, dislocation is directly above the dislocation. Dislocation is directly above the dislocation Y. So this is also an unstable position. If you consider third position, this is for first position, this is for second position. And for third position, if you'll see, dislocation is again lesser than 45 degrees. So again, it is an unstable position with respect to one X. And for with respect to Y, it is also, though it is stable here, if you'll move little bit, it will become unstable again. So it is unstable at third position also. So for three positions with respect to X and Y, all are unstable positions. Which one of the following dislocation is not feasible in FCC crystal? Now, to check the feasibility, we have two conditions. That is, the Berger vector should be conservative. B is equal to B1 equal to B2 plus B3, or B1 plus B2 is equal to B3. Either of the conditions should be satisfied. If this condition is satisfied, we need to check that B1 square should be less than B2 square plus B3 square. That the formed Berger vector should have the lesser energy, and b1 square plus b2 square. And now if you'll check the Berger vector 1 by 2, this is a sum of 1 by 2, 0, 1 bar 1 gives rise to 1 by 6 of 2 comma 3 bar and 3. So it is 0. Same. So 1 by 2, 1 by 2. So it is 2 comma 0 comma 0. This gives 1 1 bar 0. This is not feasible. Sum is not equal to this one. And in third condition, 1 by 6 into, you just double this into 2 by 2. You get 3 and 3 and 0. This is equal to 1 by 2, 1 1 0. This satisfies, it is feasible. And 1 by 2, 1 bar 0 1 be equal to 1 by 6, 3 bar 0 3. This is also equal. So only B vector is not satisfying this. So this is not feasible in abscissa equation. And the correctness of otherwise of the following of assertion reason questioning. Low alloy steels used for medium temperature creep resistance often have high addition of strong carbide forming elements. During creep deformation, the particle have high misfit and lose coherency. The particles have higher misfit with the matrix and lose the coherency. Okay, the low alloy steels which are used for medium temperature creep have addition of strong carbide forming elements. But why these are used is not the reason for this has an higher misfit but losing coherency and during creep formation. The reason is not correct. The one is true, but reason is not. The study creep rate, the study creep rate of material increases by a factor of 30 when the temperature is increased from 890 Kelvin to 990 Kelvin. The creep rate at a temperature of dash Kelvin will be 5 times the creep rate of at 890 degrees centigrade. So if you'll consider study creep rate, this is proportional to exponential minus Q by RT. So E dot S1 by E dot S2 is equal to exponential minus Q by R into 1 by T1 minus 1 by T2. This is equal to, the creep rate is 5 times the exponential minus the Q by R of. So for first time, the creep rate increases when it is 20. So for 20, exponential minus Q by R into 1 by 890 minus 1 by 980. So solving this, you get Q from here. So using this Q, you can use it here such that uh, 1 by 5 is equal to exponential minus Q by R into 1 by T minus 1 by 890. So let's solve this. You get temperature as nearly 940 Kelvin. The answer is 940. Okay. Nothing but you put ln here, you send the exponential here, you'll get ln 20. Ln 20 into r divided by 1 by 180 minus 1 by 190. You get q here. Putting that q here, you'll get 1 by 5 equal to, so it is ln 5 equal to that q value by r into 1 by t minus 1 by 890. So you get 940 Kelvin. The crack growth, the crack growth is being continuously measured in a test specimen subjected to constant amplitude cycle stress with a mean stress of 0. The crack growth rate is related to stress intensity range of delta K. dA by dN is proportional to delta K cube. So now, when the crack A is A is a crack length and N is the number of cycles, when the crack length increases by a factor of 2, the crack growth rate should increase by a factor of. So you know delta K is equal to delta sigma into root pi A. Here only the tensile stresses are considered. You won't be using compressive stresses. So whenever compressive stresses are given, you no need to consider that sigma 2 minus sigma 1. No need to consider the compressive stresses here. So delta K is proportional to A power 1 by 2. dA by dN is proportional to delta K cube. So this is proportional to A power 3 by 2. So now dA by d of 1 by dA by dN of 2 is equal to 1 by 2 whole power 3 by 2, which is nearly 2.82. So the crack growth will increase by a factor of 2.82. Thank you.